Okay, we're going to continue on here. Organic chemistry is topic. We're going that way, I think. Yes. There's like a lot of options up here. So if you do walk around, do not knock anything over. Yes, be careful of the cords. All right, we've talked about organic chemistry, which is the study, right, of carbon-based compounds. And remember that in organic chemistry, the basic connection that we have is carbons attached to carbons. And really attached to those carbons are hydrogens. And again, they could go very long, they could go kind of short. It could continue in this sort of pattern. And these are what are sometimes referred to as hydrocarbons. And hydrocarbons, much like the name implies, are really just carbons and hydrogens together in an organic sort of compound. They are non-polar, as the carbon-carbon bond and the carbon-hydrogen bond are also obviously non-polar. There are different functional groups, as we started talking about a little bit, and that sort of develops as we sort of exchange out some of these hydrogens for other elements, like oxygen, maybe nitrogen, and so forth. We talked about saturated hydrocarbons, and saturated hydrocarbons basically occur with alkanes. And alkanes are the simplest organic molecules you have. They basically have the carbon-carbon single bond. And what a saturated hydrocarbon is, as we talked about, is basically the maximum number of hydrogens that each carbon should have. Remember that it's really important as you're doing the organic there, that remember that carbon should only have 4 bonds, so never more than 4 bonds. And pretty much in organic chemistry, once you sort of run out of elements in sense of carbon and other elements, everything else is really hydrogen to get that carbon to 4 bonds. So you put really the appropriate amount of hydrogens to do so. We talked about some different types of structures. This again is what is sometimes referred to as the expanded structural formula, where you really kind of draw out all of the hydrogens. We could also have the condensed formula, where you basically don't draw out the hydrogen. So something like this is the condensed formula. We also can have a line structure. So I'll do a little bit more than 2 carbons, but I'll do a few more. And typically line structures are really just that, lines. There's really nothing else written. The only time you will ever see something else written in a line structure is if it is not a carbon. So if there's a line to something that's not a carbon, they will put the element in there. But if there is no anything else written, it's assumed that there's carbons in each of those locations. So again, that's a carbon, that's a carbon, that's a carbon, that's a carbon, and this one's a carbon, which means this guy really has 5 carbons. So remember that as well, the hydrogens are not included in line structures. So again, this guy at the end would have 3 hydrogens to get it to 4 bonds. Guy in the middle would have 2 to get it to 4 bonds. Same thing for this guy, and same thing for this guy. And again, the guy at the end would have 3 hydrogens to get it to 4 bonds. So again, line structure, just strictly pretty much just lines. Again, even if you see another line sort of off of it and nothing written there, that's assumed to be a carbon that would then have 3 hydrogens attached, which is a methyl group like we talked about. So if it wants something there, it definitely will in line structure. So, you know, if it wants something that is not a carbon, it will just write whatever it is there, and you will definitely see it. We talked about alkanes, and as we talked about last time, those alkanes are really the most important thing for us in here. Those first 10 alkanes, in terms of both their name and their formulas, are really important. And they do have a general form of CnH2n plus 2. And again, that gives you sort of the number of carbons, which is what N is. And it lets you figure out how many hydrogens that carbon should have. And again, just to run through those first 10, CH4, which is 1 carbon, and 4 hydrogens is methane, ANE. 2 carbons would have 6 hydrogens, that is ethane. 3 carbons is 8 hydrogens. That is propane. 4 carbons, 10 hydrogens is butane. 5 carbons and 12 hydrogens is pentane. 6 carbons and 14 hydrogens is hexane. 7 carbons and 16 hydrogens will be heptane. 8 carbons and 18 hydrogens would be octane. 9 carbons, which would give you 20 hydrogens, will be nonane. And lastly, 10 carbons, which would have 22 hydrogens, is decane. This is typically how a lot of organic functional groups are named, based on the name of the functional group is sort of how we name those guys. And as you can see, each one of these are all carbons attached to carbons, which have single bonds. And again, the hydrogens are attached to the carbons in each of these cases. So again, propane would look something like this, where we have our 3 carbons attached to each other, all single bonded, and our hydrogens attached like so. These are really important. As we talked about last time, pretty much everything is named based off of these 10 alkanes. So all the other sort of organic molecules and stuff that we're going to come across, they all reference back to this. And it's really about the longest carbon chain will sort of match one of these guys. And that's sort of the base of the name. For other organic compounds, we simply just sort of replace the ending, or a little bit different in terms of how we name it. But the basis of everything is really how many carbons there are, and it should match one of these guys. We sort of jumped into a little bit of the naming aspect of it, and we typically will follow the IUPAC naming, which is the International Union of Pure and Applied Chemistry. It's sort of the formal way to name things. And when we do it for alkanes, there's several rules we want to follow, and it kind of is the same rules for most things. Always we want to start with the longest carbon chain. And remember that we want to check all of our options. It may not be always the straightest. It may go straight, go up and go over, or it may go straight, go down and over. So you do want to check all of your longest sort of options for the carbon chain. And that would really give you sort of like the base of the name. It should match one of those 10 alkanes. Then remember that everything that is really not part of that longest continuous carbon chain is considered a group that's attached. And most of the groups that are attached will be what are referred to as alkyl groups. Those are basically a fancy way of saying carbon-containing groups. And they will be the exact same as our alkanes, except that they will be missing one hydrogen, as we talked about last time. The reason they're missing the one hydrogen is that will give it an opportunity or a way to attach to the longest carbon chain without giving that group too many bonds to the carbon. Again, we have to kind of remove a hydrogen to allow it to bond in. If we keep the hydrogen, it will have too many. The group names, if you remember, are named basically the exact same way, except that they will end in YL. So something like a CH3 group has 1 carbon, which is based off of methane, is lacking 1 hydrogen that allows it to attach. So we drop the last part of it. And again, this becomes a methyl group. Again, if you have a halogen that is a group that's attached, they're named like chloral, fluoral, bromol, iodo for iodine. So those are sort of how those groups are named. So once you have the longest continuous carbon chain, like we talked about, once you identify all the groups that are there, it's next thing that you want to do is you want to number the longest carbon chain. And the way that you want to do that is to number the longest carbon chain. And in the case of an alkane, we want to number whichever way gives the group the smaller number. So whichever way gives the groups that are attached the smaller number. Now, as we saw in a couple of examples, sometimes it really doesn't matter which way you go. You'll kind of hit the same numbers. In that case, it doesn't really matter in a sense. But if you went one way and the groups were like 2 and 3, and you went the other way and the groups were like 4 and 6, then you would want to go whichever way is 2 and 3 in terms of numbering. Lastly, once we got the numbering down, obviously it has to be numbered only one way. You can't kind of mix and match. So whichever way you choose to number is the way that you do need to number. And we want to put all of our groups first with their number in alphabetical order. And that is regardless of prefix. If there happens to be a prefix, or numbers. So you can have a larger number, but alphabetically that guy should come first, then the next group. And again, you want to go alphabetical order when you put it. Now, the one case where maybe if you got to this point and it did not make a difference as terms of which way you go to number the chain, you then would want to consider perhaps alphabetical in terms of which way you should number and give sort of the alphabetical order, the smaller number in that case, if it happens to be no difference which way you go. When you got all that together, pretty much you just got to put it together in alphabetical order. Remember a couple of things. In between a number and a letter, we use a dash, or even a letter to a number, we use a dash. Also, if you have two numbers in a row, we do use a comma between the two numbers. And also, we sometimes will use prefixes as well. And we will use prefixes like, again, di for 2, obviously tri for 3, tetra for 4. And what that means is it doesn't necessarily mean that the groups has to be on the same carbon, but they just need to be in the same compound. They could be on the same carbon, but they just need to be in the same compound, the same group. So if you had 2 methyl groups going on, you would call it dimethyl. You know, you had 3 methyl groups, trimethyl. And by the way, you would need to give the number for every one of those methyl groups, even if they are on the same carbon. So if you had 2 on the same carbon, you would have to give that number twice, which is probably where the comma might come into play as you do it. Any questions on that there? So let's just take a look at some of this stuff here as we talked about, and we'll get into most of these. Once again, this is a table, I think, from your book of our organic guys. And by the way, I think this is off by 1. All the line structures kind of go to the one below it. But once again, definitely want to learn both the name and the formula for those 10 alkanes. It's really important. We talked about some of this, so we'll go through some of this maybe a little bit quicker. Obviously, we talked about the condensed formula. We do typically still draw the dashes between, but we do not draw out the hydrogens. Also, a reminder, as we talked about, although in the sort of the condensed formula, it may appear that the carbons attached to the hydrogen, it is actually still, in this case, the carbons attached to the carbons is what the attachment is, with the hydrogens attached to those. So sometimes in condensed format, it might appear that the hydrogen is attached to the carbon. The one thing to remember why that would not be the case is clearly hydrogen could only have 2 electrons, as we talked about, so it can never be in the middle. So hydrogen's always got to really be on the outside of the carbons. It'll never find itself in the middle of 2 carbons or anything like that. If you have a lot of sort of continuous runs of something like CH2, sometimes you may even see a condensed formula written something like this. CH2 and like a 6 maybe. CH2, CH3. So in this particular case, what this means is obviously we have this, and then we basically have 6 of these CH2 units basically in a row. So this guy technically would have 1 carbon there, 6 more carbons there, 7, 8, and 9 carbons. And again, sometimes on those really long sort of runs in condensed formula, they'll put like a little bracket or parentheses around a unit that continues to repeat and a number next to it. Again, here's our expanded formula as well, where really the only difference is, as we talked about, we're just going to be drawing out the hydrogens there. This is our line structure. And again, it does have that kind of zigzag shape is how it's usually drawn. And as we talked about, that really for alkanes is because of the geometry that we see. Remember that in alkanes, because frankly, it has all single bonds, it has that tetrahedral arrangement. And that is, 109.5. And that's what gives it sort of that zigzag shape, is why you commonly will see line structures sort of drawn in that fashion. Once again, typically none of this stuff is obviously included in line structure. It is simply just lines, as we talked about. All right. Here's again some representations of some different versions of C4H10, which is butane. So if we look at this here, the molecular formula would be, we would just count up everything, 1, 2, 3, 4, and 5. So that would be C5. And really, because they're all single bonded, we could use our formula and count up all the hydrogens, and we should end up with 12 if you went around and counted up all the hydrogens. Our condensed formula, really, we just kind of break them off into units, basically. Oops, I missed that hydrogen there. Add that hydrogen in. So we would have CH3, CH2, 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 and CH3 in this case. And that has 5 carbons, nothing else attached, which means this is our friend pentane, as they are all single bonded. Any questions on that there? So once again, there, and to there. All right. So we want to write the condensed structural formula for ethane. So ethane is 2 carbons, right? So condensed formula would be our 2 carbons together. And heptane would be 7 carbons, right? That's what heptane means. So if you wanted to, you could just write the carbons first. It looks something like this. 1, 2, 3, 4, 5, 6, and make sure you got the right amount there would be good. And remember that if there's nothing else attached, everything else should be hydrogens. Once again, to get each carbon to 4 bonds. Guy at the far right has 1 line coming in, which means it needs 3 hydrogens to get the 4. Guy next to it there has 2 lines, which means it needs 2. Guy next to it also has 2 lines, needs 2. Same thing with this guy, and this guy, and this guy. And the guy at the end has only 1 line, so he does need his 3 coming in. And again, this would be our condensed formula for heptane, where we do not draw out, obviously, the hydrogens. Any questions on that one there? Now let's talk a little bit about cycloalkanes. Cycloalkanes are alkanes where basically kind of the end of the chain comes together and basically makes what is sometimes referred to as a ring type structure. A lot of cycloalkanes will end up being more line structures, typically how they're drawn. They actually have a general form of CnH2 times N for cycloalkanes. And that is slightly different than regular alkanes, and that is because we're making an extra bond. So when we pull those carbons together, we do have to sacrifice 2 hydrogens. So that's why it's not +2 at the end there. We need to. Oh, remind me later. Go. All right. So that is why we have to not have the 2n plus 2. Again, in organic, as we talked about, pretty much every time we sort of make another bond, in order for carbon not to end up with too many bonds to it, we do have to sacrifice carbon. So if we were to make like a double bond, we would need to get rid of 2 of those carbons to do so. If we made a triple bond, we would also get rid of 2 carbons, and it always 2 hydrogens, and it always comes from opposite carbons. So we never lose 2 hydrogens from the same carbon. It's always a hydrogen on each carbon that basically goes away. So for example, we got rid of both of those. We then could make our triple bond here and have 1. So the same thing happens, for example, if we wanted to take this carbon and kind of stitch them together to make our cycloalkane. We can't just connect them like I just drew there. Otherwise, again, that carbon will have way too many bonds. So we do need to lose basically a hydrogen on each of those carbons. And that's what we end up with. This is the condensed formula, weirdly drawn, for cyclopropane. It is still based off of the 10 alkanes. It still has 1, 2, 3 carbons, which means it is based off of propane. It's in a ring structure, so it's called cyclopropane. And most of the time, it probably would be more of a line structure where you would just see it as like a triangle drawn. We would also perhaps see like a square. The square would be what? How many carbons? 4, which is butane in a ring structure. This would be cyclobutane, right? We also have this guy here, which is 5 carbons. By sort of connected to the lines, then that would be cyclopentane. And go here, I think. This guy here would have 6 carbons, and that would be cyclohexane. Each of these will be missing 2 hydrogens from its sort of straight chain alkane. Again, here, if we looked at our butane versus cyclobutane, again, this guy has basically 2 hydrogens at each of those corners and our 4 carbons. And that means it has only 8 hydrogens in that case, which is what you get when you do this, right? 8. As opposed to if we had our straight chain, which would have 1, 2, 3, and 4, and we would have 3, 5, 7, and 10 hydrogens in our straight chain of butane. So once again, those hydrogen on each of the carbons at the end are sort of sacrificed as it kind of connects and makes that extra bond. Any questions on that? As you can see, in terms of the name, we just really add cyclo to the beginning of it. In terms of stuff attached, if there is something attached, we would just add it in. So we had something like this, and again, just say a line at the end of it. The main part of this would be obviously our triangle, our 3 carbons. And again, that is cyclopropane. And if we had something there or nothing written there, that's going to be, once again, a methyl group. So this would be putting that together, methyl cyclopropane. In this particular case, we would not need, oops, I ran off the screen there, methyl cyclopropane. In this particular case, we do not actually have to give a number where that group is located. This is what is sometimes referred to as being mono-substituted, which means there's just one group attached. And basically, wherever that group is attached is considered carbon number 1. So you don't have to actually give it. You do have to give some locations if there's multiple groups attached. So if you had, say, something like, we'll go here, maybe. Let's say we had that, and let's say we had a Cl. Take a second and see what you think you would call that there. Okay, let's take a look. So the longest carbon chain here would be our ring here. So that definitely would be our longest carbon chain, and that is 5 in a ring structure, which means really the base of our name here, I'll go up on top, is cyclopentane. We have a couple of groups attached here. We got a line right about there, and we got this group right there. Remember, a line with nothing written in it in line structure here is really a one carbon group, which as we know is a methyl group. And obviously this line has something at the end of it, which means that is what's at the end of it, which would be a chloral group in this case. So what's left to do here is we do want to give some numbers since we do got multiple things attached. So let me just kind of get rid of some of this here. So in this case, alphabetically, right? Which one should come first? Chloral. So we probably in this case would want to start with the chloral as carbon number 1. Now we could go clockwise, which obviously would give the methyl group 2, 3, 4, 5. Or we could go counterclockwise in this case, which would give the methyl group a 2, which seems like a much smaller number, obviously, than going around the other way. So this would be something like 1 dash chloral dash 2 methyl, and I'm going to try to join them. There we go. Methyl cyclopentane in that case. Yes. Question on that. So if you do have sort of multiple attached, perhaps alphabetically is a good way to kind of start with the lowest number. And then really in this case, you can go either way, clockwise or counterclockwise, whichever way will give those group the smaller number. Any questions on that there? All right, so we want to give the names here. First one is what we call that guy. It is a line structure, and it is how many carbons there. Let's just see. We got 1, 2, 3, 4, 5, 6, 7, and 8, right? And there's clearly nothing else attached there, right? So 8 carbons in a row would be octane, as there is no, they're all single bonded, obviously, so they would be an alkane. This would be kind of like the guy we just did there. That is 1, 2, 3, 4, and 5 carbons. And that is based off of pentane, but this is not a straight chain of 5, right? This is a ring structure of 5, which means this would be our cyclopentane. Once again, nothing else attached, so we would just basically just add cyclo to the beginning of pentane. Any question on that one there? All right, so we probably have done these over the run here, but just to make sure, we got 1, 2, 3, 4 carbons, nothing else attached. So that would be butane. We obviously just talked about our triangle here. So that is 1, 2, and 3 attached, or 3 carbons. Again, that's propane, but in a ring structure, this would be cyclopropane. This is a bunch, 1, 2, 3, 4, 5, 6, 7, and 8 again, with nothing else attached. This would be octane in its condensed formula. And in this guy, we got 1, 2, 3, 4, 5, and 6 carbons, which is based off of hexane. And again, in a ring structure, this would then become cyclohexane. Yeah. Any questions on any of those names there? All right, so we talked about kind of substituents. Substituents is a fancy way of saying basically groups that are attached. And remember that those groups will have one less hydrogen to allow it to attach if it is a carbon-based group that is there. Let's talk a little bit about isomers, though. Isomers are things that have the same molecular formula, but structural isomers will have some different sort of attachments and arrangements. And for example, here is butane, and this is really just a 4 carbon run. 1, 2, 3, and 4. Nothing else really attached but hydrogens. So that would be butane. And it would have 4 carbons and 10 hydrogens. This guy right here still also has 4 carbons and 10 hydrogens. So they do have the same molecular formula, but they are a little bit different. As we talked about, we are looking for the longest continuous carbon chain. So once again, in this particular case, it is actually only 3 carbons in a row is the continuous carbon chain or longest continuous carbon chain. That means unlike butane here, the base of our name here is going to be propane because of that. We obviously have one group that's attached, and that is a 1 carbon group, and that is going to be a methyl group. And if we numbered our carbons, carbon 1, carbon 2, carbon 3, again, no matter which way you go, it will put that methyl group at carbon number 2. So this is what is known as 2-methyl propane. That is a different name than butane, and that means that I actually have drawn a different structure. And those two would be isomers of each other. Remember that just because you may draw it differently or it may look different to you, doesn't necessarily mean that it is an isomer just because you kind of drew it different. So for example, if I had something like this, longest carbon chain in this case is how many? Longest carbon chain is still 4. 1, 2, 3, and 4. 4 carbons is butane. Is that an isomer? It is not, because that name is butane. The first guy's name is butane. It's just drawn differently. It's the same thing. So it's not an isomer. In order for it to be an isomer, a good way to check that it is an isomer, it needs to have a different name. So this would not be an isomer. If I did like something like this. Would this be an isomer? This would still be, what's the name of it? Yeah, this would still be butane as we go 1, 2, 3, and 4, and we're out of stuff, right? So although it may look very different, it is still butane as well, and not an isomer either. So sometimes when people are asked to draw isomers, they just figure, well, I'll just kind of draw it down, draw it up. It kind of looks different. So really the way that you want to make sure that it is different is to name it. And if you do get some different names, that provides you name it correctly, obviously. So if you do get different names, then you probably drew an isomer. If you end up with the same name, even if it looks different, you probably basically just drew the same thing. So it's really important when you do isomers that you don't do that. So there you go. Draw 3 isomers for pentane. Okay, let's take a look. So clearly the easiest one to do would be obviously perhaps 5 carbons straight ahead. There, 4 and 5. We'll add in our appropriate hydrogens to get carbon 2, 4, something like that. Yeah. Then maybe we want to mix it up a little bit. Do a little this action maybe. Add my hydrogens there to get everybody to 4. I need 3. Well, maybe just 3 in a row here. Maybe do a carbon there, maybe a carbon there. Add some hydrogens. And let's just see, let's just do like just for fun. This. All right. Did I draw 4 isomers? No. How many isomers did I actually draw? 3, I hope. Let me see. So let's start with this one. Clearly 5 in a row, nothing else there is going to be pentane, right? What would be the name of this guy? Longest carbon chains, how many? 4, which is this guy right there, right? By the way, you could get a couple ways. You could go straight and then up to get the 4. That's going to be butane as the base of the name. We then will have a 1 carbon group, which is a methyl group at carbon. What number should it be in this case? Should be 2 going right to left. 1, 2, 3, 4. Because if I went the other way, 1, 2, and 3, which is a larger number. So we would want to go this direction here to circle. That would then be 2 methyl butane squished together. There we go. So 2 methyl butane. And how about the last one here? Longest carbon chain is, it is 3. You could get it multiple ways, right? So that is 3, which means that the base of the name here is going to be propane. We then will have a methyl group there, a methyl group there. That's 2 methyl groups in this compound, which means I need a prefix of dimethyl, right? So it's going to be a dimethyl. And I also need some numbers, and those groups are at carbon number 2. Again, no matter which way you go, I do need 1, 2, or 2 2s. I do need 2 2s, I think. So that's 2, 2 dash. I'll just go above it. Dimethyl propane in that case, yes. So once again, even if the groups happen to be on the same carbons, you just give the number twice. And we would use a comma between the 2 numbers, and again, a dash, obviously, whoops, going into this one. What's the name of this guy? It would be 2 2, because that's the location of where those methyl groups are on the carbon. So this is carbon number 2 here on the main chain, and that's where we find this group and this group located. Yeah. So really, naming is all about just telling somebody where you can find everything, and it's about what number on the main carbon chain you find all these groups that are attached. It's really what the naming part is about. Other questions? Top guy would be called what? Top guy here would be called 1, 2, 3, 4, and 5, which is pentane, not an isomer, right? So it's just pentane drawn differently. Any questions on that there? All right. Yeah.
It says structural isomers. The butane by itself. What this is saying is an isomer, but you're saying it's not.
This one here, it's an isomer to this one, and these 3 here are isomers. The one on top would also be called pentane, right? Which is the same as this guy, which means they cannot be isomers of each other because they're the same thing. In order for them to be the same thing, in order for them to be different things, they would have different names.
By itself, if there's only one pentane, would be considered an isomer. If we call it 2 the same thing, it's not an isomer.
So I think to answer your question, yes. If your question is, if you're given several structures and you go to name them, and 2 structures, even though they may not look the same, end up being called pentane, is how you would properly name them, then those 2 would not be isomers of each other. They would actually be the same thing. I think that was your question, yeah?
Yeah.
Okay, yeah.
Yeah, it's by itself.
By itself, it's pentane. If you knew how to draw some isomers of it, 2-methyl butane would be considered an isomer, and 2,2-dimethyl propane would be considered isomers of each other, which means if we count up the molecular form for all these guys have 5 carbons and 12 hydrogens, if you count up them all. Yeah. And again, they are different things. Other questions? Okay. So as I mentioned before, we sort of jumped into this a little bit earlier, but again, our carbon-based groups are alkyl. We take out the ANE of the alkane name, has 1 less hydrogen. We put the YL in there. And then again, for our kind of halogens, that is how we go about naming our halogens, as we also talked about, fluoro, chloro, bromo. There are a couple of groups that are sometimes called something different, and a popular one that you should know is this one. It does come up a lot. This is what is referred to as the isopropyl group. And isopropyl is based off of a propyl group. So let's talk a little bit about sort of what the difference is between these things. And it has to do with where they actually would connect into the main chain. Now, when we talk about carbons, we could actually classify carbons as either being primary, secondary, are tertiary carbons. So they're sometimes abbreviated 1, 2, and 3 with a little circle for primary, secondary, and tertiary in terms of carbons. What does that mean? It means that if you look at a carbon, one way you could do it is to count how many carbons are directly attached to it. So for example, if I have this carbon attached to this, then we'll just do hydrogens here. This carbon has how many carbons directly attached to it? 1. This would be what is referred to as a primary carbon, has 1 carbon attached. If I had this carbon, and we'll just do hydrogens here, this carbon would have how many carbons attached directly to it? 2. This would be what is referred to as a secondary carbon. And as you could probably imagine here, this carbon here has 3 carbons that are directly attached to it, which would make it a tertiary carbon. So the difference between sort of a propyl group, a normal propyl group is sometimes called, and an isopropyl group is actually the carbon at where it attaches to the chain. This is a normal propyl group, sometimes called N-propyl. It attaches to the chain right here at this carbon. And this carbon right here is a primary, secondary, tertiary carbon. That carbon with the arrow is a... How many carbons are directly attached to it? I feel like I got all the numbers there. So yeah, that was good. So let me draw this out. Let me draw this out expanded here, just the propyl group. And it looks something like this. And like this. So once again, this carbon has how many directly attached to it? No, directly attached. 1. Yeah, it's just that guy directly attached to it, right? This guy is attached to that guy. That would make this the primary carbon. So if you have the attachment of that propyl group through the primary carbon on either side, by the way, is a primary carbon. The guy on the left-hand side also would be a primary carbon if you turned it around. You get a propyl group. Now, if we look at this guy, which is the isopropyl group, and once again, I will draw it out maybe. The attachment's actually coming from that center carbon, and that center carbon is attached directly to how many carbons? 2. That would be a secondary carbon. So the attachment in the isopropyl group actually comes through the secondary carbon, which is why it has a special name known as isopropyl. Maybe isopropyl alcohol has an OH at the top of that, and that's what isopropyl alcohol is, rubbing alcohol. So that's one you should know. CH3 is the isopropyl group. This is what is referred to as an isobutyl group, sometimes referred to also as tert-butyl, because it's attached to this carbon would be what type of carbon? It's attached to how many carbons directly? 3. This actually is a tertiary carbon, that guy. And that's why it's sometimes referred to as T-butyl as well, which is sort of tertiary butyl group. So we can classify our carbons, and depending on the attachments, you may get some different sort of groups. This is sort of a historical name, this guy here, this one as well. But we will probably come across isopropyl more than the other one. So add that to your list of sort of groups that you should be familiar with, because it will. Longest continuous carbon chain, and in this case, I think it's just straight across. So we'll go 1, 2, 3, 4, and 5, if I count correctly there. I guess that helps. So 5 carbons going to be our basis of pentane. You could do some other ways, but you will get less than 5. If you go straight then down, you got 4 carbons pretty much as your only other option. And that obviously is less. That then means that we do have some groups there. That is going to be a Cl group, which is a chloral group. We also have our 1 carbon group there, which would be our methyl group. We then want to number this right. So if we went left to right, that'll be 1, 2, 3, 4, and 5. So going sort of in the red direction here, we would have groups at 2 and 3. If we numbered the other way around, that would be 1, 2, 3, 4, and 5. Going in kind of the blue direction, we would have groups at 3 and 4. In this case, which way should we go? Yeah, we should go with the red direction there. It is as simple as 2 is smaller than 3. Yeah, so that's basically as simple as that. That means we will stick with the red numbering going in this direction. That means that my chloral group is going to be at carbon number 2. My methyl group would be at carbon number 3. And now we're ready to put this together in alphabetical order. This would then be 2 chloral dash 3 methyl, and adding our pentane to the end will do it for us. Yeah. Any questions on that one there? Yeah. So we talked a little bit about this earlier about cycloalkanes with substituents. Again, if you have just a mono substituted one, you do not need a number. But again, if you do have more than one, as we talked about, you do need to add some numbers. We kind of went through naming here. So let's talk a little bit here about drawing from the name. So let's take a look at this one, which is 3-bromo 1-chlorobutane. Whenever you want to draw something from the name, you should always work backwards in terms of the name, and that's really the best way to do it. So working backwards, butane is how many carbons? It is 4, so we're going to lay up. And really a good way to do it is to start with just the basic carbons and nothing else. So that is 4. That pretty much takes care of my butane part of the name. Then I have really a group called 1-chloral, which is a group. So that means at carbon number 1, I should find a chlorine sitting there. Now, since you are drawing it, you could call really technology advanced in this room here. That I was going to try that, but that looked really scary. I'm not really sure what's going on over there. I felt like if I broke that, that's going to be like a bill coming my way. All right, so let's try this again. So that's going to be butane, which is 1, 2, 3, 4. All right. Maybe I'll like this one better. All right, so we got 4 there. So at carbon number 1, we do have a chlorine. As I was mentioning, you could go left or right as carbon number 1. I'm going to call this guy over here carbon number 1 for me. And since I did that, everybody else has to be numbered left to right in my case. So at carbon number 1, I'm going to put a chlorine, which will take care of that. That also means at carbon number 3, I should have a bromine. And because this for me is carbon number 1, carbon number 3 would be right about there. And I should put a bromine at that point. It doesn't matter if I put it on top. I could put it on the bottom. It really doesn't matter where you put it, as long as it's on that carbon. Now, at this point, I'm out of name. Everything else just is hydrogen, again, to get carbon to 4. So guy at the far right has only 1 line coming in. So to get the 4 bonds, he needs 3 hydrogens. The guy with the bromine, actually, the carbon has 3 lines coming in, which means it has 3 bonds. So to get the 4, he needs 1 hydrogen. This guy has 2 lines, so he needs 2 hydrogens. And the guy here at the end has actually 2 lines coming in, which means it needs 2 hydrogens. And there you go. That would be the condensed formula. So always want to work backwards, and the name is the best way of doing it. Start with just the carbon skeleton, add on all the groups that are attached, and then pretty much at the end, just fill it up with hydrogens till you get to 4 bonds. Any questions on that there? All right, let's try some here to finish it out. Good talk. All right, why don't you give the name of these guys here? Why don't I add some things to this? So let's do this. And then why don't you draw 3-ethyl 4-methyl hexane. Gonna run out of room there, huh? I'll go move it over just a little bit. We'll try it again. 3-ethyl 4-methyl, and we'll do hexane. And why don't you also draw propyl cyclopropane. We'll do that one. All right. So names the guys on the left, and you can do condensed form if you like, whatever one you want to do on the guys on the right. Okay, let's take a look since we're getting to the end and see how you're doing. We'll start with this guy. So clearly here, our box is our longest carbon chain. So that is going to give us a little cyclobutane as S4 carbons. We have a chloral group there, a bromol group there. So probably want to start numbering right about there as 1, 2 gives us the smallest number. So a 1 bromol, 2 chloral cyclobutane. Yeah. Any question on that name there? Coming to our line structure, remember that wherever there's sort of an end or where two lines come together as a carbon, so that's 1, 2, 3, 4, and 5 carbons. Looks like our longest continuous carbon chain there. So that 5 carbons means that pentane here will be our base of our name. That also only leaves one group there, which is a chloral group. And if we went to number here, you could probably see going right to left should give us obviously the smaller number. If we went the other way, we'd probably have a 4, which is larger. So this would be 2-chloropentane. Any question on that one there? Longest carbon chain on the bottom there is going to be, looks like we'll just go straight. 1, 2, 3, 4, and 5. If you went down and then up and up, that's only 4, I believe. 1, we went kind of this way. That's 1, 2, 3, 4. That's not enough. If we started over here, 1, 2, 3, 4, and 5. So that's the same as going the other way. So we might as well stick with going 5 straight. Looks like the longest. We'll get rid of some of this here. So the 5 straight will still be pentane as our base of this name. We have really a line here and a line here. Each of those lines is what group? Is a methyl group, right? Because it's missing a hydrogen. And we do have 2 of them together. So I'm going to steal that methyl I wrote on the bottom there. So that's going to be a dimethyl situation. And we do need to do some numbering. In this case, left to right, right to left. Which way? Yeah, left to right will give us the smaller numbers 1, 2, 3, 4, and 5. So that is a 2,3 dimethyl pentane. Yeah. Any questions on that? Obviously, if you went the other way, you're looking at 3, 4, which is obviously a larger number. Any question on any of those names there? All right, let's draw these here to finish. We will go backwards. So hexane is 6 carbons. So that's what I'm going to start with. 1, 2, 3, 4, 5, and 6. Stay on there. Good. That takes care of that. At carbon number 4, I need a methyl group. So once again, I'm going to call this carbon number 1 for me, which means carbon number 4 is right about there. And it is a methyl group, which is a CH3. Takes care of that. And at carbon number 3, which would be right next door to the left, is an ethyl group. That is a 2-carbon group, right? I'll just go that way since I'm running out of room. That takes care of that. Everybody else is hydrogens here. So guy at the far right needs 3 to finish him up. That is a 3 there off the screen. The guy to the left of him needs 2. Guy to the left there needs 1. Guy to the left also only needs 1. Guy to the left there needs 2. Guy at the very beginning needs 3. Now I even left the hydrogens off of my ethyl group, right? So I could finish those out the same way. That has 2 lines, which means I need 2. And this guy has 1 line, which means I need 3. Yeah. Any questions on that one? And again, this guy over here is a 3. Hard to see off the screen there. Lastly, here we have cyclopropane. So propane is 3 carbons. Cyclo tells us it's a ring structure. So if you want, you could do like a little line structure if you want. If you want to do more of the condensed structure, it would look something like this. I really shouldn't put the hydrogen in, but that would give us our cyclopropane. Then it should have a propyl group, which is a 3 carbon group as well. So if you wanted to, again, you could just add it in like this and add in your hydrogens, which would give us 2, and this guy would need 2 in this case. If I did it on my other one there, which was condensed, I actually do need to get rid of a hydrogen at one of these guys. Otherwise, he will have too many. And I could put it in, say, to this guy, my propyl group. And again, I do need to get rid of that hydrogen. Otherwise, that guy would have too many bonds. Any questions on that there? All right, we'll lay that up there for now.